From the MIT Energy Initiative, this is What If It Works, a podcast looking at the energy solutions for climate change. I'm Kara Miller.
And I'm Rob Stoner.
And today we talk with a materials scientist about the stuff in our buildings, our phones, our cars, and how that stuff takes a toll on the environment.
Materials and the manufacture of materials are responsible for over a third of greenhouse gas emissions globally. And so the choices we make at every stage of designing materials, of recycling and manufacturing are going to have global impact.
That's Elsa Olivetti, professor of materials science and engineering at MIT and mission lead for the Decarbonizing Energy and Industry mission of MIT's climate project. And of course, there's long been discussion in business, amongst policymakers, about emissions. What should or shouldn't be coming out of our cars? How detrimental are the emissions from airplanes? But Olivetti says there's a whole other dimension to that emissions conversation.
So those cars and those airplanes are made of stuff, right? And so we've got to do a lot to make that stuff. You think about what we sometimes call the embodied impact of the stuff that we hold and we, process and live in and throughout our lives. And it's also surprising maybe for people that that's dominated, that impact, that 1/3 is dominated by a couple of key materials that we produce at vast scales, right? Steel, cement, we make as much cement as we use water, right? So the sort of scale of that, aluminum, copper. So these kind of really big bulk materials are a big part of that impact.
And remember, when you turn raw materials into, say, an airplane, there are a ton of steps. Where do we tend to expend the most energy? Olivetti says it depends, but there's a lot of energy involved in the refining process.
So going from an ore and the chemical and heat and temperature processes that are associated with making them usable in whatever form. And so that's when we're talking about greenhouse gas emissions. If we're talking about land use or the environmental impact on an ecosystem or water quality, then the burden might be shifting to a different stage of the life cycle, more in the mining, because of the significant amount of wastes that are produced or the releases to water, air, and soils.
And that gets at an important piece of this. As significant as greenhouse gases are, the effect of materials extraction on the planet reaches even beyond that. Take tailings, which exist on the sites of mines, and they're essentially just a bunch of the stuff that people weren't really looking for.
So tailings are a processing waste from the mining and refining process. And the thing that to think about with tailings is it's most frequently wet because we add a lot of water and solvents to try to float up the parts of the metal and the constituents that we actually want.
Mines will often have these huge ponds containing tailings, and they're filled with chemicals. And as we transition to a cleaner energy system, we will need to do more mining. So how do you make that mining and the refinement of raw materials more efficient and less dirty? That's what drives Olivetti. And she says it's important to recognize as technology gets more advanced, our needs are changing.
One thing to keep in mind as we are thinking about transitioning to low carbon energy infrastructure is that particularly the technologies that are needed for that are particularly dependent on a wider variety and more of the materials that we use. So something like a car with an internal combustion engine may have a couple of materials that are specialized for that engine. But if we think about a battery electric vehicle, for example, there can be upwards of 5 to 8 times the quantity of more specialty minerals and a much broader array. So things like nickel and cobalt and lithium and graphite that are very critical to the battery itself. And we need more complexity in terms of more supply chains that we're accessing. And then we also need more quantity.
As we transition to electric vehicles, does that mean more mining has to go on to support electric vehicles than to support internal combustion engines?
Yeah, more mining of that broader set,
Broader set
right?
of
I mean,
materials. Okay.
in terms of the so we have significant growth associated with a much wider variety of minerals.
Okay.
And upwards of 100% full increases in the
Wow.
quantities that we need to be going after, and that there's more complexity associated with those. And that's really across all the energy technologies, that advanced technologies that we're interested in, right? And Rob's been talking about more specialty minerals that are present in magnets, for example, in wind turbines, but I mentioned a couple also for batteries and solar cells. So you can think about that the low carbon energy transition is dependent on a significant minerals extraction situation. It's dependent on us doing the mining and beneficiation and mineral extraction in a thoughtful, sustainable, sensible way in order to have that transition happen without a series of unintended consequences that we want to make sure that we're developing policies and incentives to directionally look at. And I can talk a little bit more specifically about one of those, just as an example. Sure. We could dig into talking about nickel. And nickel is interesting for a couple of different reasons. It's important to remember that the things that are the dominant uses for nickel now are not necessarily what is relevant to the energy transition as much. So nickel right now is used the majority for stainless steel, something we think about and use all the time. But it's also a critical element associated with battery electric vehicles. And so the transition for our vehicle fleet that needs to happen as part of a low carbon energy transition is going to mean there's a lot more nickel that we'll need. And so that will start to become the dominant use, which is pretty significant in terms of what that means for supply chains. And the other thing that's interesting about the broader set of materials that we need in part of the low carbon energy transition is that they have different kinds of geographic concentrations than we might expect. They could be very highly concentrated in particular geographies, which means we're very dependent on those geographies for the mining process. It also downstream, as I said, in refining and processing. So in nickel's case, the majority of nickel extraction, one region that nickel extraction happens is in Indonesia. It's also extracted in Russia. So the demand for nickel is growing so rapidly that there's been a pretty significant investment in mining infrastructure in Indonesia, both in terms of new sources, new mines opening, but also Indonesia is interested in the economic development opportunities. So they also want to be developing infrastructure downstream of extracting it out of the ground. They want to develop that capability to refine and beneficiate, as we've talked about.
So that they get to add the value in their home country rather than having someone else do it and get the money for it.
Exactly. Like they have been historically taking that ore and digging it out of the ground, but then shipping it elsewhere to be refined. And the majority is actually currently refined in China. And that's true of almost all of the materials we could talk about after the mining. Mining is sometimes, while geographically concentrated, different kinds of geographic pockets for mining, but almost all of it is currently processed and supply chains go through China as we're talking downstream. And in Indonesia in particular, what's been challenging is thinking about the trade-offs of the environmental impact of mining with the economic development opportunity and their need and interest to grow rapidly to take advantage of this opportunity.
Yeah, I grew up in a mining town in northern Canada, Sudbury, Ontario. And in those days, it was sulfite minerals that they mined in hard rock deep below the surface. And we were always aware that Indonesia was coming along and would have the ability to mine their laterite nickel deposits. But those are surface deposits. And as Elsa's saying, getting to those deposits means you're leveling forests and removing huge amounts of earth. And there are other places where that kind of thing exists. New Caledonia is another place in the South Pacific. We were always, feeling very smug about our sulfites because we didn't have to cause that sort of destruction. We caused other kinds of destruction. And so we were pretty sure that would never happen. And now I'm seeing, even looking beyond laterites, people are talking about nickel nodules on the ocean floor. And they're not only talking about mining nickel that way, but scraping huge amounts of ocean floor in order to get at new minerals. I'm really kind of uncomfortable with that, and I think we have to think about that as a society. There's a lot of discussion.
I feel like anybody listening to this discussion right now, their head is kind of exploding because we're talking about using more nickel to facilitate the transition to cleaner energy, like have electric vehicles, not have internal combustion engines. And to do that, you need to clear cut forests, potentially scrape the ocean floor, use like a ton of processing, right? Or ship stuff to China and process, and
which we already do,
right? And so I guess my question is, are we sure all this pollution and greenhouse gas emissions is worth it to facilitate the electric vehicles? Like, I assume somebody has done this math. Right?
Yeah, we actually just did this analysis looking at those materials that I said, these sort of bulk, high volume materials, which are the majority of impact, right? We can't forget that. The kind of nuances and complexities of all these supply chains are very critical and very important part of it. And we must transition to low carbon modes of transport, modes of generating electricity. Each of those are very dependent on this broader portfolio of materials I've mentioned. But in terms of the volumes, we also need vast quantities of concrete, steel, copper, right? All of these bulk materials as well. That whole set is necessary as part of the transition. And the production from an energy perspective of all of those materials that are part of the energy transition is still about half of the energy that would be required to continue the fossil fuel-based energy infrastructure that we have.
Even if you consider that, like in Indonesia, obviously, it sounds like some forests are being cut down, and that has like long-term ramifications when it comes to, absorbing carbon, doesn't it?
Yeah. So all the growth as an economy is inextricably linked to resource use.
Right.
The things we do and the systems in which we exist are dependent on impact on the environment. And I think the trick and the opportunity we have in a low carbon energy transition is, while we're thinking thoughtfully about the technology we need, about the impact we're doing, we can make sure we're not having significant unintended consequences. And one of the things that's interesting about the new kinds of pressures and the new geography shifts that's happening is it's different kinds of pressures in different kinds of regions. And that then lead to other challenges we need to be tracking. So in the case of Indonesia, this fast tracking of nickel production and processing is an opportunity nationally for Indonesia, but we need the right kind of signals, the right kind of investment, the right kind of signals from demand, from consumers, from automobile manufacturers of let's do it right, and what are the resources in order to do it right, so that we're not having these trade-offs. Instead, we're building sustainable supply throughout the entire life cycle of those materials.
Is that happening? Like, as we have more electric vehicles, as the Chinese are producing tons of electric vehicles, are the right incentives reaching Indonesia, or are people just like, go, find as much nickel as you possibly can, and we'll pay you for it and do it as fast as you can?
We can say a little bit of both, or a lot of bit of both. But we need to try to think about what is the full suite of decarbonization opportunities to apply throughout the life cycle, but also other ways in which we would mitigate the environmental impact of resource use. Yeah, so we can work with the Indonesian government, for example, or the automobile manufacturers to try to develop sustainable supply chains and demand signals that would propagate throughout those supply chains for more sustainable production. We can also think about ways to incent production domestically or in where we have more control over those supply chains. Other strategies could include increasing recycling, and so which would maybe in the long run mean that we need less primary extraction. So there are a couple of different strategies for managing those trade-offs.
Yeah, there are some processes that are forming around the COP and UNFCCC that try to create a way for developed countries with money to help developing countries that are producing these minerals get cleaner. And the process that's most talked about now is called the JET-P process, Joint Transition Energy Plan or Program, I think it's called, where different wealthy countries are contributing money, but there are strings attached. If you want to, we will give you money for energy development in India, for example, says the United States or Japan to Indonesia, provided that you don't develop coal mines and instead develop these low carbon resources like either solar or hydro, and perhaps also adopt refining practices that are less energy intensive or inherently less polluting. And I think we're at the beginning of that sort of move toward those sorts of arrangements, but it's a possible way.
Have you been, either with nickel or with any other thing that is mined for, have you been on the ground at one of those mines, and can you talk about what it's like? Since so few people really have that experience, what's it like?
Yeah, I've been to a couple of mines, and I think the part that is consistently shocking is the vastness of it, the scale at which things need to operate in order to get the materials that we use. And for example, I've been to the copper mine in Utah, Kennecott mine, that it's been operation since 1900. It's it's open pit, incredibly 2 Empire State Buildings tall pit in the ground. Wow. And you can see this tiny little truck at the bottom that is an enormous truck when you're standing next to it. The wheel is, I can't even see the top of the wheel if I'm standing next to the truck. Wow. But it looks like a tiny like Lego
toy. Yeah.
As it's coming up, spinning up the spiral of the mine, and kind of rock pile after rock pile, and the vast majority of what is being driven out of that on that tiny then becoming bigger truck is rock that doesn't contain copper. That isn't necessarily part of this. And you can see in that site in particular, you can go from each of the stages down to even some of the wire manufacturers are local, within driving distance of that, to see that. So that's probably the most striking, is the vastness and how much activity goes into each molecule that we then get to use in our cell phones, that we just don't even really think about as we're living our daily lives. And the other thing that's striking is we think about decarbonizing and that trying to reduce our reliance on fossil fuel, how much of that process still is going to need fossil fuels in order to transition, right? That truck is using fuel. And so I think that this sort of importance of moving rapidly but thoughtfully in what we talked about in nickel or in gate, you can think about in any of these sort of local community conversations that need to happen within mining. It's a particular challenge that engaging communities and thinking about those processes as they're happening locally has to happen deliberately and rapidly because of the scale and the need of the transition, all the way from every battery in our vehicles to the grid, but also that truck that's driving out of the mine.
That also brings you into contact with society more. I mean, some of the easy places are easy because they're far away from where people live and want to be. But as you start pursuing deposits of higher grades or any grades that you can get access to, you often come into contact with, for example, Aboriginal groups. In Australia, this has been a major factor in the Pilbara area in Western Australia for mining iron. And Rio Tinto, one of the big operators there, had just a disaster with one of those mines where they inadvertently destroyed a major cultural heritage site. And so those sorts of complications introduce complexity in developing the mines, planning them, operating in those areas, and that adds to cost as well as just the sort of having to move more rock.
Rob, you were saying you grew up in a mining town in Canada. I wonder if you think that the mining industry has changed a lot. in your lifetime?
I know it's a lot safer now than it used to be, at least in developed countries. When I was a child, we had a lot of orphans in my classes, typically going through primary school. People had lost their fathers in the mines. A lot of amputees. I had a cycling coach at one point who had lost a leg in a mine collapse, and there were lots of stories of mine collapses. That happens far less nowadays because of the safety culture that these companies have developed. But I don't know how well that translates to environments like Indonesia or other poor countries where people are prepared to take bigger personal risks and maybe look the other way in order to get a job.
Or just the central government has fewer regulations about, like, you have to, whatever. They may not have an OSHA, like, these are hurdles that you have to overcome to be licensed or whatever.
Yeah, and less automation. They're using manual labor in many situations where we would use machines. Right. So people are more exposed.
Elsa, I don't know if you have any thoughts there, but I also wonder if you can talk a little bit about when you think about cell phones and electric vehicles, what are the metals that we need more and more of? Like, if you had to say these are really on the rise, like if you look forward 10 or 20 years as like these are the things where the demand is just really rising because our lives are changing. Like, we didn't use, like, people didn't have cell phones 30 years ago necessarily that they carried with them. So what are EVs that,
Yeah, there are a couple of elements that are more prominent within the electrification or low carbon infrastructure. We've talked about some of them. So cobalt, copper, nickel, lithium. Then there's also the set that are as part of wind turbines and solar, so neodymium and other rare earth elements that are present, but things like molybdenum, so there's a plethora of those. But another way to think about it is when you're talking about cell phones. In 1980, there was something like 11 elements that were used within the circuit board for a phone, and now it's the entire periodic table.
Wow,
really.
Okay.
And so essentially, you are carrying around stable forms of the primary periodic table in your pocket, and so that's just from 1980. And in the 2000s, we added another 45, and it just has grown. And those elements are there for a reason. They add a particular functionality. They perform better. We want that performance as consumers. We don't often think about the trade-offs associated with the supply chains of those, but also the complexity that introduces in terms of trying to do something with them when we're done with our cell phone. So it's ubiquitous. And also, in addition to that, the fact that there's many more different types, there's also just more associated with it. So silicon is another element that we think about, both relevant for energy transition in solar cells, but also relevant in wafers for electronics and electrical appliances.
Are there any of those elements where you think, I'm really worried, like that I don't think there's enough of it? When I see the demand curve and I see what I think is the supply, I don't see it. Or I'm worried that these things are going to collide.
So we often say that materials availability is not about running out. It's about risk associated with those trade-offs. So we talked about the sort of rapid rise in nickel and, what does that do for local communities? Because often we'll get it at whatever price, at whatever cost. Another way to think about this is those that kind of catalog this. So the U.S. Geological Society, for example, has this way they frame the amount that we are, the reserves, the amount that's economically extractable divided by the production, the amount that we need annually. And that's kind of how much is left, right? And so 40 years ago, we had 40 years of copper left based on that.
Okay.
Now we have 40 years of copper left. And that's because as the demand goes up, there's technology that increases our ability to extract them. So I don't think about it as running out, but you think about it as these significant shifts or volatility in prices in supply chains, in what does that mean for local communities, in the levels at which we're willing to go in order to extract these materials, and then what the complications are that introduces that. On one side, we've talked about the environmental impact, but we could also think about it on the demand side. What are we not doing because it's gotten too expensive, right? And what does that mean for the fact that we wouldn't be able to electrify the vehicle fleet at the rate we would want to because the prices of those materials are going up? Okay. And that's another thing that starts to happen with the advanced energy technologies is as we get better at doing them, the manufacturing cost goes down, making the battery pack, making the solar cell, but it starts to be very dependent on then what the prices of those materials are. And so subject to the kinds of supply chain disruptions that mean when we have actual or perceived risk of supply availability constraints rather than it running out.
You used the word primary metals at one point when you were talking earlier. And that's a really important subject, I think, because, you mine for iron, you mine for nickel, you would make a nickel mine, you'd make a copper mine, but you'd never make a strontium mine or yttrium mine. A lot of those are byproducts of all that mining. As we use more and more of these advanced technologies, big magnets, strong magnets, for example, or even fusion systems that use some of these exotic materials or materials that we don't commonly find. Do we hit a wall with those where the primary production no longer keeps up with demand for these sort of secondary metals or co-produced metals? And do we sort of stop using them and run into disasters?
In terms of the other kinds of risks associated with materials availability, there's a particular kind of risk or a particular kind of dynamic associated with those metals that we're not building the mine for, as you say. And cobalt, which has been talked about a lot in the press in terms of the challenges in mining and the geographic concentration, is an example that we don't build a mine for cobalt. We build a mine for nickel or copper. And the cobalt is obtained as a byproduct of that, as you're saying. And so what that means is for things like cobalt, as demand goes up, it's not necessarily having the same kind of price response that we would have in nickel or copper, for example. So we're kind of subject to what's happening with that nickel mine. So that introduces a different kind of volatility in the supply. Sometimes the sources for these materials are in wastes. So vanadium, for example, is something where there's a lot of opportunity for other vanadium extraction in secondary streams that we wouldn't normally.
What is vanadium? I've never heard of it.
It's an element.
It's an under the radar.
But it's used in steel and a lot, and very dominantly. And it offers a lot of really important properties in steel, but it also could be relevant to some kinds of battery technologies, flow batteries.
Vanadium flow batteries. Yeah.
In fact, it could be, that's another way we could do more electrification storage on the grid, for example.
I'm reminded of a famous situation a couple of years ago where demand for steel increased dramatically in China because of subsidies for building, which created tremendous demand for vanadium. Okay. And it wiped out all of the guys who were trying to make vanadium flow batteries. And so there was an interesting, crossover from one
I see, because it was
another.
Like pulled away for this other use, and then people
those batteries
couldn't.
That's actually a really important point to make back on our nickel story, because we've been talking about the sort of demand signals of how do you create sustainable supplies of nickel. Right. Because I said earlier, most of the nickel right now is used in stainless steel. We also have to talk to the folks that are part of the stainless steel supply chain. If we're just working with the battery manufacturers and they're sending all sorts of demand signals, let's get sustainable nickel, but we don't talk to the folks sending signals from the stainless steel industry, then the nickel miners don't care because they're answering to the stainless steel folks now. So that dynamic of what is the dominant use right now, but then how will that change? And how fast will that change is really important when we start to try to think about how do we incentivize, what sorts of policies are we going to write.
So let's talk about solutions. And you could use nickel or anything else, but maybe talk about one element and how you see kind of how you move the needle in a way that you feel like would be a win? Like, how do you make it so there's fewer greenhouse gases coming from the extraction of that thing, the processing of that thing?
So we could think about copper a little bit, because copper is interesting in that it's pretty dependent to any kind of growth, both in terms of electrification, but also just in terms of electronic devices and our increased demand for that, and just the need to conduct more electrons. Copper's a good way to do that.
So it's in like all our laptops and our
cars
phones.
And
okay.
The dominant use is actually in buildings and construction, wiring in our buildings.
Okay.
And the infrastructure associated with that. So it's kind of everywhere.
Right. So cities are increasing in size, which they are, then you're building buildings.
Yeah, so copper is ubiquitous. So you could think about the environmental implications of copper if we're focused on energy and greenhouse gas emissions. There's ways of thinking about solutions across the supply chain. So we could think about the production of heat to run the processes, and could we electrify that? But also, can we change the chemistry of how we go from the mineral to copper? We could look at different kinds of ways of doing that are more environmentally friendly. So sulfidation is a process being looked at here at MIT in terms of better processing of copper and to the products that we're interested in. But you could also think about reduction of mining overall by increasing the recycling of copper. And recycling can be challenging to think about in all the stuff that we've talked about before, because as we're increasing demand, we are still growing in the amount of material that we use. And so there isn't enough existing to be pulling out for recycling to meet that demand, right? So recycling offers an opportunity to displace mining really only if we've saturated what's being used, we sometimes say in stock or in the buildings that we're using. But some things like copper and steel, as I said, because it's ubiquitous, because it's everywhere, those elements, those materials offer an opportunity for more circularity.
And we do that in the United States. I mean, there's a lot of scrap steel used here.
Exactly. Scrap steel and scrap copper, where in the case of copper, at least, there's still a lot of hidden stocks that we aren't necessarily collecting or recycling as much as we could.
Like a building gets torn down. You mean that kind of thing?
Exactly. Construction demolition waste, where we're not recovering all the copper that can be used again in those applications.
How do you incentivize people to do that rather than say, yeah, it's cheaper to go to some poor country and get new copper out of the ground? Like, labor isn't very expensive. It's doable.
Yeah. So it's tricky. You have to build up the infrastructure for recycling, and that is actually happening right now in the copper conversation in the U.S. Because of the growth in demand and the fact that there could be more of this demand met by secondary. We have to invest capital in building secondary refining processes for copper in the United States or wherever, or in Europe, in order to make that happen. And then, as you point out with your question, there's then incenting the collection of that material so that it can then be sent to those refiners. And so there's this trade-off there between, do we have enough capacity to process the secondary material, and is the value of copper, is the price of copper high enough that we're interested, that there's support to set up the collection infrastructure to do that. And most often, it will need some kind of subsidy to incent that to start off with. And even in countries like China, there's significant subsidies in making secondary work to kind of start it off, and often to continue that until we're able to have the processes themselves be economic relative to the primary processes.
How do we do in recycling of metals? I mean, are a lot of them ending up in dumps?
You mean landfills? The U.S.?
We, the U.S. Well, we maybe other countries too.
Yes, we are certainly not doing as well as we can. So the recycling rates for things like copper is usually about 30% of consumption is met with secondary. That could go up. We've looked at that copper in particular. That could go up to maybe about up to 60% reasonably economically, but we need the local capacity to develop that out. And so, generally recycling is around 30 to 40% for most metals in that range. It's higher for things like steel. And going down to something pretty kind of fundamental that we all think about, something like an aluminum can, even there's just significant headroom to increase recycling. And there we have pretty direct evidence that deposits on an aluminum can, in terms of, we usually say, increases the amount of collection rate. So in the US, is where the highest is sort of 10 cents, right? We would think for redemption, you have, upwards of 40, 50% recovery based on that. But in Europe, in some European countries where it's higher, the bottle deposits are higher, the recycling rate is also higher. So there's some pretty direct feedback loops there that can, we can use to build stronger policies for incenting that as well.
It seems like, though, what you're saying is, government is extremely important if you're thinking about recycling more and more of these materials that we have floating around versus digging them out of the ground anew. And yes, I immediately thought of soda cans because you see people like collecting them to get back that money. And it makes complete sense that if you have like the demolition of a building and there's a bunch of copper in there, the more you offer to go in and like grab that copper out, the more likely it is, like the higher that price is, the more somebody's like, okay, I will do this because it's worth my time.
Yeah. And so you have this model where you have to try to think about how do we incent that? And some of the policy schemes start to look like responsibility going either to the individual or to the producer. So there's a set of incentives in recycling called extender producer responsibility, where we think about those that are manufacturing to begin with, the wire or the bottle, or then, have a cost associated with then managing that at end of life. And so then it's, where does that cost go? Who bears the burden of that cost? And being thoughtful about architecting that policy is part of the need there.
Elsa Olivetti is professor of material science and engineering at MIT. She's also mission director for MIT's climate project, Decarbonizing Energy and Industry. Elsa Olivetti, thank you so much for being here.
Thank you for having me.
Thanks, Elsa.
What If It Works is a production of the MIT Energy Initiative. If you like the show, please leave us a review or invite a friend to listen. And remember to subscribe on Apple Podcasts, Spotify, or wherever you get your podcasts. You can find an archive of every episode, all of our show notes, and a lot more at energy.mit.edu/podcasts. And you can learn more about the work of the Energy Initiative and the energy transition at energy.mit.edu. Our original podcast artwork is by Zeitler Design. Special thanks to all of the people at Mighty and MIT who make this show possible. I'm Kara Miller.
And I'm Rob Stoner.
Thanks for listening.